Hey guys, just gonna make a quick video to help you out a little bit. I know we have kind of a weird beginning of this unit, but I think you'll feel confident with sequences in series, especially this first lesson. So first, it's things that you've done before. Write the first 5 terms of a sequence. So we have a sub n equals 2n plus 1. So it's just a matter of plugging in, n equals 1 the first time, and calculating that out, and then doing the same thing with 2, then 3, then 4, then 5. So you can see I went ahead and show my work here to give you a visual, and it's just a simple sequence of 3, 5, 7, 9, 11. A little arithmetic sequence that we'll talk about more later on. Then the next one we have is we have this -1 to the n power, which you'll see a lot with this -1 to the n is going to make it kind of an alternating sign, which we'll talk about more later on in the notes. But same exact procedure, plug the 1 in for n, then 2, then 3, then 4, then 5, because we're looking for the first 5 terms. It's just a matter of computing that out. So this one kind of alternates between 3, then 1, 3, then 1, then 3. So it's kind of an interesting sequence. So I'll let you guys look at this one. We have a division, we have a rational type look for our sequence, and we have another alternating between 1 and -1. And so I'm just going to pause the video just like we were in class and see what you can do on your own, and then I'll let you check the key. Alright, so the next one we're going to talk about is recognizing if we were given a sequence of numbers, what's the best rule or providing an nth term for the sequence, an expression that would fit that particular situation. This is really the main reason why I wanted to make this video. Because I wanted to explain, what's going on here. So at first you can see that it's increasing by 4 every single time, and since our numbers are the exact same, they're 4 right here on the very first time we do a difference, we know that that's going to be 4n. And so there's a lot of different ways you can go about it from here, but just to keep things simple for right now, so if I were to say 4 times 1, because 1's our first term, well, we would be at 4, so we need to take 3 away in order to get to 1, our actual first term. And then I could check it again. 4 times 2 is 8. 8 minus 3 is 5. So that'd be our second term. If you're trying to find our third term, same thing. 4 times 3 is 12. Minus 3 is 9. And you can check every single one of those numbers. It says up here in the instructions, apparent, quote unquote, and that's really an important comment, because technically speaking, the sequence goes on. We can just have a short visual of this, so it's using a pattern recognition. It's definitely inductive reasoning, and not we can't say for sure that's a sequence, but I think you understand what I mean by that. This one's interesting. This next one, it's actually on your notes. On your notes, there's another one in between that, and you can go ahead and take care of that on your own. I think you'll see the pattern you're looking for. Are we adding or subtracting? Are we multiplying, dividing? And I'll let you do that one on your own. So this one, I believe, is actually your third one in this little section example. And it's interesting because there's not like an apparent multiplication of any kind or division. It's definitely alternating signs between positive and negatives. So what I did here is I just went and wrote the sequence again and say it was just all positive numbers. So I did my first difference. And you can see it's the difference between 2 and 9 is 7, and then 9 and 28 is 19, and so on and so forth. And I found that first differential. Obviously, these numbers are not the same. So what I did again is I said, okay, let me find the differences again. So from 7 to 19 is 12. The difference between 37 and 19 here is 18. Then we go up 24 more to get to 61. Once again, these numbers are not the same. If we did one more difference, the difference between 12 and 18 is 6, and 18 and 24 is 6. We find now we have two numbers, they finally have a repeat of differences. So this is really referred to as finite differences. If the numbers are the same on the first level, like our first problem, then that would be a first degree polynomial. So we can see it's n to the first power. If they'd been the same number on the second level, then it'd be a second degree polynomial, which means it'd be quadratic in nature. And in this particular problem, it was our third level, and since the third level is where the numbers are the same, it's going to be a third degree polynomial. So you can see in my sequence right here I have n cubed, since I know it was the same on the third difference, the third finite difference. So now we have n cubed is established. So if you were to plug in 1, for instance, and cube it, and if you add 1, now we're back at 2. If you plug in 2, our second term in our sequence, and cube it, that'd be 8. 8 plus 1 is 9. You can continue to do that. 3 to the third plus 1 is 28. 4 to the third plus 1 is 65. And then obviously 5 to the third plus 1 is 126. So we've now developed this blue sequence right here, 2, 9, 28, 65, and 126. And so what I did here in the front is want to make sure that it's alternating signs. So this -1, like we talked about earlier, is going to help us do that. So if you were to plug in 1, for instance, for n, well, 1 minus 1 is 0. -1 to 0 is 1, so we know it's not changing it. But the moment we go to our second term, that would be 2 minus 1, which is 1. -1 to the first power is -1. And then -1 times, remember it's our second number, so it'd be 2 cubed plus 1, will give us our -9. And if we continue to go through our sequence of numbers, it'll just continue to alternate between positives and negatives, and now we have the original sequence that we were trying to find. Okay, so the next thing I want to talk about was recursive sequences. And I know there's been some issues with this particular. I've heard so many of you say that recursive is not something necessarily liked. And I'll probably get into it a little bit more as far as maybe even going back and forth between recursive and explicit. But just a good introduction, at least for today, is just take this little sequence over here. So it says that a sub 1 equals 6. Okay, that basically means our first term is 6. And since the instructions ask us to find the first 5 terms, we've already gotten 1 taken care of here. So I'm just going to go down the list. We're going to try to find a sub 2. Okay, so what I looked at is, here's our rule. A sub k plus 1 is equal to a sub k plus 1. Alright, so k plus 1 I put right here. And I went ahead and put this 1 in red. So 1 plus 1 would be our second term, which is what we're looking for, because we already had our first term. Okay, so that's equal to, well, it says a sub k. So if k plus 1 is 2, that means that a sub k would just be a sub 1. Alright, let me try to say this a different way. We're plugging in 1 in place of k, which does produce 2. But since we put 1 in place of k here, we're also going to put it in place of k here. If that's a little bit unclear, let me know, and I can definitely come around and answer those questions for you to help you out. But here's a sub 1 now, plus 1. Well, we already know what a sub 1 is. We found that was given to us at the beginning. It's 6. So now we can say, okay, 6 plus 1 is 7. And so what we're going to do is, now that we have 7, to find the next term in our sequence, that's when we plug in 2 now for k, both those spots. Well, 2 plus 1 would be 3, so in order to find our third term of our sequence, we're going to use the previous term, which in this case is 7, that value, so the previous term's value. So a sub 2 is 7, so plug it in right here. 7 plus 1 is 8. They're going to repeat the process. We can take the previous number, which is 8, add 1 to it and get 9. Take the previous number, which is 9, add 1 to it and get 10. And what we'll have a discussion in class is some pretty well-known sequences that fit this model. But I want to wait for everyone to be involved in that particular discussion. So I'm going to pause the video for a moment and just give you an opportunity to see if you can get part B. Take your time, pay attention to those values, and then check the key. Hey, we're back. So now factorials. Factorials are going to play a pretty big role in this unit. It's a pretty cool little mathematical concept. If you had n factorial, basically you're just going to say, and the way it's written here at least, is you're going 1 times 2 times 3, and continue to go until you get to that particular n value. Now what I do is I actually flip it around. I think of it more as, and you can see this example I gave, if I said something like 9 factorial, I think of it more as 9 times 8 times 7 times 6. I just keep on multiplying until I get down to 1. So on part A here, I just went ahead and wrote it 9 all the way down to 1 with all those different products. I did the same thing with 3 factorial, 7 factorial. And so I have all these numbers multiplied together. And so what I'm going to do is just evaluate this. So I'm going to do my best here to try not to produce a Shigan. But we have all of these values, 7 factorial, represented right there. Well, those would all divide out. So we've now simplified 7 all the way down to 1 with 7 all the way down to 1. So all we're left with now is just 9 times 8 over 3 times 2 times 1. And that's just a simple simplifying, which I'll let you go ahead and finish out. I just wanted you to see kind of how I did this process. Same thing over here. So we had 3 factorial, 8 factorial, that product over 4 factorial times 4 factorial. So I went ahead and wrote everything out so you could kind of see it. So you can just see some pretty quick simplifying as we have 4 times 3 times 2 times 1. We can simplify those out. So now those are gone. And you can break them down however you want to. You can maybe say you want to, since it's all multiplication, maybe you want to take out the 3 factorial. So we could take out that 3 factorial by breaking up this 4. So now we just basically have 8 times 7 times 6 times 5. That's the remaining numerator values divided by our one remaining denominator value of 4. And once again, I can let you simplify that out. Last one's part C. This one's pretty cool. It's n plus 1 factorial over n factorial, so giving you just a little bit more generalized approach. But I went ahead and wrote it out. N plus 1 times n minus 1. And just continued on until we got to 1. Did the same thing with the denominator, except with n's. And you probably see it already. Well, this entire thing right here is n factorial, and we have n factorial represented in our numerator as well. So those are simplifying out, which leaves us with n plus 1. And I'm kind of doing this on my computer, otherwise I'd write it. But here's our remaining answer, which you can look at the key if you want to see a little bit better structure with that. Awesome. So this one I'm going to let you try. Let you check the key. The only thing that might throw you off is they want you to begin with n equals 0. And when we do sequences in series, sometimes you might begin when n equals 1, sometimes you might begin when n equals 0. But either one of those typically serve as our initial values. And so for this particular problem, I want you to use 0 as your initial value. And so I didn't want to throw you off. When you plug in 0 for n, I'll just go ahead and tell you that 0 factorial equals 1. And then consequently, if once you get to 1, and you plug 1 in for your next term, well, 1 factorial is also 1. So we have two values that give us 1. We're not dividing by 0. And that way you can finish that particular problem out and list out the first 5 terms. Alright, so I went ahead and jumped over to the key for these next ones. Unfortunately, I can't be writing as I'm teaching. Sorry about that. We had to get out of there due to the bad weather, but I wanted to go ahead and show you, the sigma notation and kind of how it works, which you typically have as a value that's given below. And so you can see it's kind of hard to see on this, but hopefully your notes it's better. It says I equals 1. Okay, and we're going from I equals 1, and we're going to continue to plug in, kind of like we did at the beginning. We'll plug 1 in and get that particular value. So you can see how I did that. Plug 4 times 1 plus 1, which is 5. And then we'll plug in 2 and do the same thing. 4 times 2 plus 1, which is 9. And we'll just continue to plug in, increasingly numbers with the sequence. So 1, then 2, and then 3, until we've obtained the number of terms that we're supposed to. So when do we stop? Well, you go from 1, increasing by 1 each time until you reach this number at the top. So in this case, we're going from 1 all the way to 4. And so after you plug all those numbers in, this notation right here, sigma, means to sum those numbers, so to add them. So you can see we took 5, 9, 13, and 17, and we had a sum of 44. So the next ones I gave you over here are 2 plus k cubed, just different rule or expression given. This time I want you to start at 2, and we're going to go all the way until we get to 5. So those particular values you can kind of see. See if I can get this covered here. So plug 2 in, 2 cubed is 8, plus 2 is 10, and just continue on until we get to, after we plugged in 5, into K. So there's where 2 is plugged in, 3, 4, 5. Found that sum is 232. Okay, let's do one more here. 2 over I factorial. So if you did 2 over I factorial, well, you plug in 1 factorial, you can see it'd just be 2 over 1 factorial. If you plugged in 2, that'd be 2 over 2 factorial, which 2 divided by 2 is 1. If you plugged in 3, that'd be 2 over 3 factorial, which is 3 times 2 times 1. So 2 over 3 times 2 times 1 is 6. And just continue that process until we get to 6 factorial. So 2 over 6 factorial will be 720. And then that sum is simplified fraction 1,237 over 360. Alright, final problems. So we have a sigma, a summation again, 5 over 10 to the n equals 1 to infinity. So this is actually going on forever in essence. So what I've done here is I've broken it down into find the third partial sum, sixth partial sum, and then the actual sum, which we'll get to. So the third partial sum just basically means let's add, okay, in this series of numbers, let's add 3 terms. Okay, so one thing I failed to mention that I do want to go ahead and say right now, a sequence is just simply a list of numbers, whereas a series is taking those particular numbers and maybe adding them together. Okay, so it's taking a sequence, a pattern that we recognize, and then finding the sum. And there's different types of series, and there's a lot of cool things you guys are going to do later on, but in essence for right now, they'll kind of serve as a good definition. So part A, find the third partial sum. Like we said, we're going to find 3 terms in a sequence of numbers, and then due to sigma notation, we're going to add them. So I went ahead and listed those out. Let me hide this out right here. So from n equals 1 to 3, because we're looking for third partial sum, be 5 over 10 plus 5 over 100 plus 5 over 1,000. And I think I went ahead and listed out those as a common denominator. And then when you add all those up, 555 over 1,000. Okay, so the next thing that I did was I took the 6 partial sum. So now we're going to go from n equals 1 all the way to 6. Alright, now to shorten it up a little bit, I just went ahead and said, well, the first 3 terms we found earlier, so I just went ahead and put that fraction here at the beginning. So this sum right here, 555 over 1,000, that fraction rather, represents our third partial sum. So our first 3 terms add together. And then we have this particular one, which is when we plug in 4 for n, and then 5, and then 6. So there's our 6 partial sum. Did the exact same process as before, found a common denominator, summed all those numbers together, and there's the fraction that we obtained. Now, I didn't simplify these, and I did that on purpose because I wanted you to be able to see some things. First of all, I'll go ahead and show you those decimals, which you guys probably already know. And you can probably see a pretty easy pattern that's happening right now. So if you're trying to find the actual sum, say we continue to do this forever, all the way to infinity, well, that would produce 0.5 repeating, which as a fraction is 5 over 9. So this 5 over 9 is pretty cool. When you have a number divided by 9, a lot of pretty cool things happens, and we'll get into those discussions later on. So hopefully this video is helpful for you. For Mitchell and Drew, we'll see how many Shigans I got even in this video, and we'll see what the over-under was on that. If you have any questions, let me know. Thanks, guys.